This video, we're going to talk about intermolecular forces of liquids and solids. The learning competency for this video is to be able to describe and differentiate the types of intermolecular forces. The specific objectives are the following. Before we go to the intermolecular forces, we have to review some of the concepts. Let's review the kinetic molecular theory. To summarize, it states that all matter is made of tiny particles. These particles are in constant motion, and the speed of these particles is proportional to temperature. This means that the increased temperature means greater speed. Solids, liquids, and gases differ in distances between particles, in the freedom of motion of particles, and in the extent to which the particles interact. Also remember some of the states of matter. We have solid, liquid, and gas. We have already studied gases. Now we will only focus on solids and liquids, particularly the properties of liquids. Solids and liquids are called the condensed states. Now let's recall some of their properties. We have five different properties in this table. First, we have volume and shape. Volume is the amount of space that a substance or object occupies or that is enclosed within a container. We also have density, which is the mass per unit volume, followed by the motion of molecules. Next, we have compressibility. Lastly, we have thermal expansion. Another concept to remember is the phase change. The state a substance is in at a particular temperature and pressure depends on the kinetic energy of the particles. Again, when we say kinetic energy, it is the energy that a moving object has because of its motion. The energy stored in an object due to its position is called potential energy. We also have the strength of attractions between particles. So converting a gas into liquid or solid requires the molecules to get closer to each other, which means cooling or compressing the gas is needed. Now, converting a solid into liquid or gas requires the molecules to move farther apart, means heating the gas or reducing the pressure on it. So for example, propane on your LPG. Propane is stored in tanks at temperatures above 2.7 atmospheres, which turns it into a liquid. When the valve is opened, some of the propane evaporates into the gas phase. Okay, you have here the propane gas and the propane liquid. Let's start with the ion-ion interaction. This is actually ionic bonding, okay, present in ionic compounds. Ionic compounds in general are solids at room temperature with relatively high melting points. For example is sodium chloride. It has a melting point of 801 degrees Celsius. We also have potassium chlorate, which has a melting point of 356 degrees centigrade. Okay, so from Coulomb's law, the product of the charges Q1 and Q2 in the numerator is always negative. That is why salts are always more stable than the isolated cations and anions. Okay, so the distance d for ionic compounds is the sum of the ionic radii. Thus, some trends in melting points can be predicted from trends in ion radius. Okay, remember that atomic radius decreases from top to bottom. Why is this important? It's important for you to recall this so that you will be able to compare the properties later. Now let's relate the kinetic molecular theory to the intermolecular forces. We have said that atoms or molecules can stick to each other, right? For example, we have hydrochloric acid molecules or HCl. We know that this hydrogen atom and this chlorine atom are covalently bonded because they are non-metals. If we have another HCl molecule here, they can attract each other in a weaker manner. Okay, we call it intermolecular attraction. The prefix inter means between, so it's literally between molecules. This covalent bonding is within the molecule, so we call it intramolecular attraction. Remember that the attractions between molecules are not nearly as strong as the intramolecular attractions that hold compounds together. They are, however, strong enough to control physical properties such as boiling points and melting points, vapor pressures, and viscosities, which we are going to study in the next video. These intermolecular forces as a group are referred to as the van der Waals forces. Now, what's the difference between intermolecular versus intramolecular forces? Intramolecular forces operate within each molecule, influencing the chemical properties of a substance. For example, covalent bonds. Okay, they are very strong forces which result from large charges interacting over short distances. So remember in math, here in the Coulomb's law, if you're dividing a high number to a low number, you'll get a high quotient. So high energy. Now, intermolecular forces, on the other hand, operate between separate molecules, influencing the physical properties of the substance. These are forces that hold liquids and solids together and influence their melting and boiling points. They are weaker forces because they result from smaller charges or partial charges interacting over much larger distances. So, for example, to break an OH bond in water, the water must be heated to thousands of degrees Celsius. Meaning, to completely overcome the intermolecular forces, all you have to do is boil it, right? At 100 degrees Celsius. Now, the question is, why can melting points and boiling points of substances be used as indicators of strength of intermolecular forces operating in given solids and liquids? So, when solid melts or liquid boils, the particles move away from each other. As they do, intermolecular forces of attraction are broken. So remember, the stronger the intermolecular forces to be broken, the larger the amount of energy needed to break them. Hence, the higher the melting point for solid to liquid transformation and boiling point for liquid to gas transformation. Okay. Now we have different types of intermolecular forces. There are actually three major types of intermolecular forces. First, we have the London dispersion forces. We have the dipole-dipole interaction and the hydrogen bonding. Okay, we're going to discuss another type of intermolecular force, which is the ion dipole interaction. In some books, they say that there are only two major types of intermolecular forces, which are the London dispersion force and the dipole-dipole interaction. They put hydrogen bonding under dipole-dipole interaction. Well, it fits the definition, but there's a slight difference. So I just made another category for it. Just to give you an overview, London dispersion forces are attractive forces arising from instantaneous dipoles and induced dipoles. Okay? Dipole-dipole are attractive forces between polar molecules. Hydrogen bonding are attractive force in polar molecules containing hydrogen atom bonded to a small, highly electronegative element such as nitrogen, oxygen, and fluorine. Now, the ion dipole force is an intermolecular attraction between an ion and the polar molecule. This is an important force in solutions of ions. That's why I included this. The strength of these forces are what make it possible for ionic substances to dissolve in polar solvents. Let's start with London dispersion forces. This is also called as dispersion forces, London forces, or instantaneous dipole, induced dipole forces. Remember that all atoms and molecules experience London dispersion forces, which are attractive forces arising from fluctuations in the electron distribution within atoms or molecules. In an atom or molecule, the electrons are random motion, right? Remember the electron cloud. Now, this random motion of electrons may cause them to be clustered more at one end of the particle, giving that end a very small partial negative charge. This will create a temporary instantaneous dipole. This instantaneous dipole can create induced dipoles in its neighbors by attracting or repelling its electrons. Now let's have a closer look. Here I have two helium atoms, atom A and atom B. Helium atoms are nonpolar. I also have two views, the subatomic view and the polarization view, just for clarity. Now, while the electrons in the 1s orbital of helium would repel each other and therefore tend to stay far away from each other, it does happen that they occasionally wind up on the same side of the atom. Suppose it happened with atom B. So these electrons became closer. At that instant, the helium atom B is polar with an excess of electrons on the left side and shortage on the right side. That's why you'll have a negative and a positive charge. This is what we call the instantaneous dipole. Another helium nearby then would have dipole induced in it, as the electrons on the left side of atom B repel the electrons in the cloud on atom A. So that's why it's called induced, meaning to bring about or influence to. When the electron cloud is repelled to the other side, this will form a partial positive charge on the right side of atom A. Then atom A and atom B will interact. What you have to remember is that London dispersion forces or dispersion forces are attractions between an instantaneous dipole and an induced dipole. Also remember that dispersion forces exist between all molecules, but they are the only forces that exist between non-polar molecules. Okay? Polar molecules and ions can also induce dipoles in non-polar molecules. For example, I have here a polar molecule, water, and a non-polar molecule, oxygen. So when they attract each other, this will now form a dipole-induced dipole. Okay? A dipole-induced dipole is a weak attraction that results when a polar molecule induces a dipole in an atom or in a nonpolar molecule by disturbing the arrangement of electrons in the nonpolar species. Now, what if we have ion? This will now result to an ion-induced dipole attraction. This is a weak attraction that results when the approach of an ion, for example, iron ion, induces a dipole in an atom or in a nonpolar molecule by disturbing the arrangement of electrons in the nonpolar species. London forces are generally small with energies in the range of 1 to 10 kilojoule per mole. The exact magnitude of London forces in molecules depends on the polarizability of the molecule. Polarizability is the ease with which a molecule's electron cloud can be distorted by nearby electric field. Polarizability increases with the size of the atom or the molar mass of the molecule. This will lead us to larger London forces and higher boiling points. So what are the factors that affect London dispersion forces? First is the number of electrons in an atom. More electrons, there are more dispersion force. Next, we have the size of atom or molecule, or simply the molecular weight. The larger the atom is, more electrons to slosh around, easier to polarize. For example, here in this table, as you increase the number of carbon, you increase the molecular weight. And if you notice, the boiling point also increases. The same with the noble gases and halogens. The noble gases and the halogens which have higher molecular weight have higher boiling point. point. Another factor that affects London dispersion forces is the shape of the molecules with similar masses. All of these molecules are isomers of C5H12, right? All of this. Therefore, they have similar masses. But the different arrangement of carbon atoms lead to a different overall shape and surface area. Okay? So remember, the more compact the molecule is, the less dispersion force it has. Therefore, the lower boiling point it has. Okay, so if you're going to look at 2,2-dimethyl propane, this one is more compact because it's almost circular. So it has lower boiling point because it has lower dispersion force. Also, long, thin molecules like this one and pentane tend to have stronger dispersion forces than short, round ones like neopentane or this one, the 2,2-dimethyl propane. This is due to the increased surface area in N-pentane. Now, just by observation, you will see that this four 9-carbon molecules has larger surface area, so it has greater LDF, right? So this is the same with fatty acids. So as the number of carbons increases in a series of fatty acids, the melting point increases. Okay? Look at the number of carbons. C11, C13, C15, C17. This is because as the number of carbons increases, the chains get longer. And when the chains are longer, the molecules are bigger. The larger the molecule, the greater the dispersion forces. When the attractive forces holding the particles together is greater, you have to get a higher temperature to break those forces. So the melting point is higher. Next, we have the dipole-dipole forces. Dipole-dipole forces are the intermolecular forces between molecules that possesses dipole moment. Okay? Molecules that have permanent dipoles are attracted to each other via electrostatic attraction. The partial positive end of one is attracted to the partial negative end of the other and vice versa. So if you're going to look at this figure, the interaction between two opposite charges is attractive. Positive, negative. This is attractive. The interaction between any two like charges is repulsive. So for example, this negative and this negative charge. So they will push each other away from each other. Okay? Take note that these forces are only important when the molecules are close to each other. So in general, for molecules of the same molecular weight, a polar molecule will have a higher boiling point than a non-polar molecule. Because in polar molecule, you have the dipole-dipole plus London dispersion forces. On the other hand, a non-polar molecule will only have London dispersion forces. So in general, for molecules of the same molecular weight, a polar molecule will have a higher boiling point than a non-polar molecule. So again, dipole-dipole forces are usually weak and are only significant when molecules are in close contact. The more polar the molecule is, the stronger the dipole-dipole forces and the higher the boiling point is. So you can see in this one. So substances with larger intermolecular attractions will require more energy to separate the particles and will therefore boil at higher temperature. Now, there is a special type of dipole-dipole attraction that occurs when a hydrogen atom bonded to a strongly electronegative atom exists in an area of another electronegative atom with a lone pair of electrons. This is what we call hydrogen bonding. For example, in water molecules, H2O, hydrogen is covalently bonded to the more electronegative oxygen atom, right? Here, the location of the bond pair of electrons in the OH is very close to the oxygen nucleus. Therefore, the oxygen atom develops a partial negative charge, and the hydrogen atom develops a partial positive charge. This is due to the large difference in the electronegativities of oxygen and hydrogen. Okay, suppose you have another water molecule in the area. A hydrogen bonding is formed between the two water molecules due to the dipole-dipole interactions between the hydrogen atom of one water molecule and the oxygen atom of another water molecule. Hence, we define hydrogen bonding as a special type of molecular attraction between the hydrogen atom in a polar bond and non-bonding electron pair on a nearby small electronegative ion or atom. So this atom is usually nitrogen and fluorine. Okay? So hydrogen is especially strong version of the dipole-dipole force that occurs in molecules which have nitrogen, oxygen, and fluorine bonds. The electronegativity difference between oxygen, nitrogen, and fluorine is so large that these bonds are so polar and the attractions between the opposite partial charges are very strong. Hydrogen bonds can actually have energies up to 40 kilojoules per mole. Okay? So hydrogen bonds are mostly strong in comparison to normal dipole-dipole force and dispersion forces. However, they are weak compared to true covalent or ionic bonds. So what are the conditions for hydrogen bonding? One is that the molecule must contain a highly electronegative atom linked to a hydrogen atom. The higher the electronegativity is, the greater the polarization of the molecule is. The other condition is the size of the electronegative atom. It should be small. The smaller the size, the greater is the electrostatic attraction. Okay? So any molecule that contains OH bond, such as ethanol, is capable of hydrogen bonds. As you can see here, the hydrogen of ethyl alcohol is bonded to the oxygen of dimethyl ether. This figure shows the effect of molar mass and hydrogen bonding on boiling points. Hydrogen bonding causes water to boil at much higher temperature than would be expected for such a small molecule. We have established when we discuss van der Waals forces that boiling point increases as the molar mass increases, right? But here, even though some molecules have bigger molar mass compared to water, it's still at the top. Water is just 18.01 gram per mole compared to 34.1 gram per mole of hydrogen selenide. But still, water has higher boiling point. Why? This again is because of the hydrogen bonding. Hydrogen bonding also causes solid water to adopt a more crystalline structure, which is less dense than the liquid structure. We will discuss this in the next video. This shows the hydrogen bonding in ice, which results in an ordered open arrangement. DNA, or deoxyribonucleic acid, the molecule which encodes genetic information in living organisms, consists of a strand of sugar molecules called deoxyribose connected by phosphate groups. Now, each sugar has one of four bases attached to it. So the hydrogen bonds between the bases in the separate strands of DNA cause them to cling together in the famous double helix structure. Okay, lastly, we have the ion dipole forces. Ion dipole forces are the result of electrical interactions or Coulombic attraction between an ion and the partial charges of a polar molecule. Okay? So these forces are responsible for the ability of polar solvents, like water, to dissolve ionic compounds. As you can see in this figure, the green one, this one, the positive ends of the polar molecule are oriented toward the negatively charged anion. Now, in this polar molecule, the negative ends, the red, of this polar molecule are oriented toward the positively charged cation. Ion dipole forces occur in mixture of ionic and polar species. They are dependent upon the size and charge of an ion, dipole moment, and the size of the molecule. Ion dipole forces can also be repulsive. One example is the hydration of cations. I have here a table to summarize the intermolecular forces and when and where do they occur. I also have some examples. So this is another summary showing the relative strength and the phenomenon. Okay, so if you want, you may take down notes or take a picture, screen capture. An organizational chart, okay, on how to determine the intermolecular forces present in a molecule or compound. First, identify the interacting molecules or ions. Then you have to ask yourself, are ions involved? If no, you should ask yourself if polar molecules are involved. If still it's a no, then you only have dispersion forces. But if you have a yes, you have to ask yourself, are the hydrogen atoms bonded to nitrogen, oxygen, or fluorine atoms? If no, you have dipole-dipole forces. If yes, you have a hydrogen bonding. Now, what if ions are involved? Ask yourself, are polar molecules and ions both present? If yes, of course it will be ion dipole forces. If no, it will be an ionic bonding, which we have discussed a long time ago. So this table summarizes the type of intermolecular interaction and when and where they occur. So you have to remember that all chemicals exhibit dispersion forces. As you can see here, you have all checks. Okay? And the strongest force dictates the extent of attraction, and that the strongest force dictates the extent of attractions between molecules. Now, when the shape of two substances have comparable molar masses and shapes, the dispersion forces are approximately equal. Lastly, when the molecules of two substances differ widely in molar masses and there's no hydrogen bonding, dispersion forces tend to determine which substance has the stronger intermolecular attractions. So, what is the relationship between intermolecular forces and solubility? It is actually the polarity which determines whether one liquid mixes with another liquid. The general solubility rule is that like dissolves like. For example, methanol and water mix because they are both polar, right? We call them miscible. They are miscible with each other, meaning they are soluble in all proportions. That's why they form a homogeneous solution. Here, octane and water do not mix because octane is non-polar. So we describe them as immiscible. So they form heterogeneous mixture. So this is also the reason why oil and water don't mix with each other. Okay, so how about the combinations of intermolecular forces? Okay, so when larger molecules dissolve in liquid solvents, more than one intermolecular force may be involved. So, as a general rule, as polar molecules become larger, they become less soluble in water. This is best described by this picture. So ethanol it's miscible, right? And if you increase the number of carbon atoms, making pentanol, you can only dissolve 2.6 grams per 100 milliliter of water. Now, octanol here is sparingly soluble. If we're going to look at the surrounding, this lighter blue color, this is what makes octanol water-loving. And this, the darker blue, are actually formed by the dispersion forces. This makes water hydrophobic or water-fearing.